Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
The 1957 paper by David Bohm and Yakiv Aharonov, titled Significance of Electromagnetic Potentials in the Quantum Theory, stands as a seminal contribution to 20th century physics, a work of profound conceptual elegance and disruptive theoretical power. Its arguments, articulated through a pair of deceptively simple thought experiments, compelled a fundamental re-evaluation of the role and reality of electromagnetic potentials within the quantum framework. The paper's enduring influence stems from the exacting rigor of its internal claims, which demonstrated that the vector and scalar potentials, long considered auxiliary mathematical devices in classical electromagnetism, exert a direct and measurable influence on the behavior of charged particles. This essay will undertake a systematic, section-by-section evaluation of the internal logic, methodology, and core assertions presented in this landmark work. It will trace the progression of their argument from the initial proposition challenging the established physical ontology to the detailed exposition of the magnetic and electric effects, culminating in the critical defense of their results on the grounds of gauge invariance. The analysis will focus exclusively on the specific claims made within the paper, assessing the coherence of their reasoning and the revolutionary implications of their conclusions for the conceptual structure of physical theory. Section 1. The initial proposition and re-evaluation of potentials. The paper commences by articulating the established physical picture of electromagnetism, a framework wherein the electric and magnetic field vectors possess sole physical reality. Within this view, the scalar potential, represented by the Greek letter phi, and the vector potential, designated A, function as mathematical conveniences introduced to simplify the solution of Maxwell's equations. Bohm and Aharonov's opening argument evaluates this long-held conception, finding it entirely sufficient for describing all phenomena within the domain of classical physics. They proceed to introduce the central hypothesis of their work, that the quantum theory allows for a new class of phenomena in which the potentials have a physical effect. The initial claim is structured as a question of completeness. The authors query whether the description of electromagnetism through fields alone remains adequate when moving into the quantum realm. Their methodology here is purely conceptual, setting the stage for the specific theoretical demonstrations that follow. They propose that the quantum mechanical description of a particle, governed by the Schrödinger equation, incorporates the potentials directly into the Hamiltonian operator. This direct inclusion, they suggest, points toward the possibility that the potentials themselves, independent of the fields derived from them, can alter a particle's physical state. The argument in this introductory section is therefore one of theoretical motivation. It skillfully frames the subsequent analysis by establishing a tension between the classical ontology of fields and the mathematical structure of quantum mechanics, which appears to grant the potentials a more fundamental standing. The authors claim that this structural feature of quantum theory is pregnant with physical meaning, a meaning that can be coaxed out through carefully designed experimental scenarii. Section 2. Analysis of the magnetic effect thought experiment. The second section of the paper presents the first and more famous of their two thought experiments, designed to demonstrate the physical action of the vector potential in a region where the magnetic field is zero. The proposed apparatus involves a long, thin solenoid, which creates a magnetic field confined entirely within its cylindrical volume. Outside the solenoid, the magnetic field, which is the curl of the vector potential A, is precisely zero. The vector potential itself, however, is non-zero in this exterior region, circulating around the solenoid. The core of the argument rests on analyzing the behavior of a coherent beam of charged particles, such as electrons, which is split into two parts. One part of the beam travels to the right of the solenoid, and the other travels to the left, both moving through the region where the magnetic field is absent. The two beams are then recombined to produce an interference pattern. Bohm and Aharonov's central claim in this section is that the presence of the solenoid, even though it is inaccessible to the particles, will induce a relative phase shift between the two beams. They provide a rigorous derivation of this effect based on the Schrödinger equation. The phase of the wave function along the given path is altered by an amount proportional to the line integral of the vector potential along that path. Specifically, the change in phase is given by the expression the electric charge E divided by Planck's constant h bar multiplied by the integral of the vector potential dotted with a differential line m and dl. When comparing the two paths, one on each side of the solenoid, the difference in their accumulated phases results in a net phase shift. This phase shift, delta phi, is equal to the electric charge E divided by h bar multiplied by the closed-loop integral of the vector potential around the solenoid. By Stokes' theorem, this closed-loop integral is equivalent to the total magnetic flux enclosed by the paths. The primary assertion is that this phase shift is a real, physical effect that will manifest as a measurable displacement of the interference fringes at the point where the beams recombine. The evidence for this claim is entirely theoretical, derived from the foundational equations of quantum mechanics. The methodology is impeccable. The calculation is a straightforward application of established quantum principles to a novel physical situation. The power of the argument lies in its stark conclusion: the electron's behavior is modified by a magnetic field they never experience. The physical agent of this change, according to the paper's logic, must be the vector potential A, which pervades the space through which the particles travel. This section successfully establishes the plausibility of their central thesis by providing a concrete, calculable example where potentials appear to have a direct causal efficacy. Section 3. Evaluation of the proposed electric effect. In the third section, Bohm and Aharonov extend their reasoning to the scalar potential, phi. They propose a complementary thought experiment to demonstrate that it too can produce a physical effect in a region where the corresponding field, in this case the electric field, is zero. The setup involves splitting a coherent electron beam and passing each subbeam through a separate, isolated conducting cylinder or Faraday cage. Initially, both cylinders are at the same electric potential. Crucially, after the electron wave packets have fully entered their respective cylinders but before they have exited, a time-varying potential difference is applied between the two cylinders. While the potential of one cylinder is raised and the other is lowered, the electric field inside each perfect conductor remains zero. The particle is shielded from any electric force. Before the wave packets reach the end of the cylinders, the potential difference is removed, returning both cylinders to the same potential. The authors claim that despite the particle never encountering an electric field, a relative phase shift will develop between the two beams. Their derivation again proceeds from the Schrödinger equation. The time-dependent part of the wave functions. Phase evolves according to the integral of the energy over time. In the presence of a scalar potential phi, the energy of the particle is shifted by an amount equal to the charge E times the potential phi. Consequently, the accumulated phase shift is given by the expression the negative of the charge E divided by Planck's constant h bar multiplied by the integral over time of the scalar potential phi. The relative phase shift between the two beams is therefore proportional to the time integral of the potential difference between the two cylinders. This phase shift, like its magnetic counterpart, would be observable as a shift in the interference pattern upon recombination of the beams. The argument in this section mirrors the logic of the magnetic case, reinforcing the paper's overarching claim by demonstrating its applicability to both components of the electromagnetic potential. The methodology is again purely theoretical, providing a logical proof of concept based on the fundamental tenets of quantum mechanics. The claim's strength comes from its symmetry with the previous example. It shows that the physical significance of potentials is a general feature of quantum electrodynamics, affecting the particle's wave function through both its spatial and temporal evolution. Section 4. The crucial defense of gauge invariance and locality. This section of the paper addresses the most significant potential objection to their claims, the problem of gauge invariance. In classical electrodynamics, the potentials are defined only up to a gauge transformation. One can change the vector potential by adding the gradient of an arbitrary scalar function, and simultaneously change the scalar potential phi by subtracting the time derivative of that same function, without altering the physical electric and magnetic fields. A physicist could rightly ask whether the phase shifts calculated by Bohm and Aharonov are merely artifacts of a particular choice of gauge, lacking genuine physical reality. The authors confront this challenge directly. Their central claim in this section is that the predicted interference effects are, in fact, completely gauge invariant. They demonstrate this with mathematical precision. While the phase accumulated along a single path does depend on the choice of gauge, the difference in phase between the two paths in their experiments is independent of the gauge. For the magnetic case, the observable quantity is the closed-loop integral of the vector potential, which equates to the magnetic flux. They show that under a gauge transformation, this integral remains unchanged. For the electric case, the observable is the time integral of the potential difference, which is likewise demonstrated to be gauge invariant. This argument is the theoretical linchpin of the entire paper. It elevates the proposed effects from mathematical curiosities to physically meaningful and, in principle, verifiable predictions. The methodology here is one of rigorous mathematical proof, securing the logical foundation of their work. Having established gauge invariance, Bohm and Aharonov introduce a subtle and powerful re-evaluation of the concept of locality. The classical view holds that physical interactions are local, mediated by fields at a given point in spacetime. Their effect appears to suggest a form of non-locality, where a particle at one location is affected by a field in a distant, inaccessible region. However, the authors propose a different interpretation. They claim that their theory actually represents a more complete form of locality. In their view, the potentials provide a more direct and local description of the electromagnetic interaction than the fields do. The particle, they argue, interacts locally with the potential that exists at its own position. The apparent non-locality arises only if one insists on the field as the sole physical entity. This reframing is a moment of profound insight, suggesting that what constitutes a local interaction is itself dependent on the choice of fundamental physical variables. This part of the paper reveals the deepest layer of their argument, a call to revise the very ontology of physical interaction in light of quantum mechanics. Section 5 Synthesis of claims and the redefined role of potentials. The concluding section of the paper serves to synthesize the arguments and crystallize their implications. Bohm and Aharonov restate their primary claim that the electromagnetic potentials, as they appear in the Hamiltonian of the Schrödinger equation, are not mere mathematical aids but have a direct physical meaning demonstrated by their ability to produce observable quantum interference effects. They assert that the magnetic and electric thought experiments, fortified by the proof of gauge invariance, provide compelling theoretical evidence for this conclusion. Their final arguments evaluate the consequences of this finding for the conceptual structure of physics. They suggest that the traditional distinction between the physical reality of fields and the mathematical convenience of potentials dissolves in the quantum domain. The potentials, they posit, should be regarded as fundamental physical quantities. This claim represents a significant departure from the prevailing interpretation of electromagnetic theory. The paper concludes by reflecting on the character of quantum laws. It suggests that the Aharonov-Bohm effect highlights the inherently non-local and topological character of quantum mechanics. The phase shift depends not on the local values of the field along the particle's path, but on a global property, the total magnetic flux enclosed by the paths. This insight, that quantum mechanics is sensitive to the topological structure of the configuration space, was one of the paper's most forward-looking contributions. The overall assessment presented in their conclusion is one of necessity. The structure of quantum theory, when taken seriously, compels this new view of potentials. The paper closes with the quiet confidence of a completed logical proof, leaving the challenge of experimental verification to the broader physics community. In conclusion, the 1957 paper by Bohm and Aharonov presents a masterfully constructed argument for the physical significance of electromagnetic potentials in quantum theory. The evaluation of its internal claims reveals a work of exceptional logical coherence and conceptual depth. From the initial framing of the problem to the elegant thought experiments for both magnetic and electric effects, the authors build a systematic case. The critical defense of their results through the principle of gauge invariance provides an unassailable theoretical foundation for their predictions. The subtle but powerful redefinition of locality further underscores the profound nature of their discovery, suggesting that the potentials offer a more fundamental description of interaction at the quantum level. The paper's claims, derived rigorously from the core equations of quantum mechanics, amounted to a successful prediction of a new physical phenomenon. The subsequent experimental confirmation of the Aharonov-Bohm effect validated the internal logic presented in the paper, transforming its theoretical assertions into established physical fact. The work's enduring legacy lies in its demonstration that even the most foundational concepts in physics are subject to revision, and that the mathematical formalism of a theory can contain deep, unappreciated truths about the nature of reality. It remains a paramount example of how a carefully reasoned theoretical argument, grounded in the specifics of an existing framework, can fundamentally alter our understanding of the physical world.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.